So up to this point, we've been doing a lot of talking about how to solve specific problem that we're going to do in homework 2. And now, in some sense, maybe this is a little bit backwards, but now we're going to go back and talk about sort of the general theory of how you solve partial differential equations in general. I've been focusing in on the specifics of an example that we were considering, which is this advection diffusion equation in 2 dimensions, which is part of homework 2. And now I'm going to take a step back and start talking about sort of a bigger picture of what you're actually doing in solving PDEs. Okay? So time and space stepping schemes. Okay, so this is going to be the sort of the start of sort of a bigger general theory. In particular, what we're going to talk about is really what's referred to as a method of lines. Okay, and you'll see how where this name comes from as we move on in the lecture. But the first note is that everything that we've done up to this point, especially with discretization, is to basically break the problem up to algebra. And in particular, if we can actually break this thing up into a system of first-order differential equations, we can just throw it into something like ODE4.5 or ODE2.3 or any of the ODE solvers. So our whole goal in life when it comes to this kind of stuff is to do exactly that. Okay? All right, so basic time stepping schemes. So let's consider a simple example. The heat equation. du dt equals some constant k times du dx squared, and that's a u, not a y. So let me take off that tail. Got a little long. Okay. And you usually typically impose some kind of boundary conditions. What I'll do now for this one here is impose something like periodic boundaries. So we're going to solve it on some domain from negative L to L. And you simply ask the question, if I start off with some initial condition, what happens? So time t equals 0, maybe I have something like this. Who knows? And then I can ask the question, start off with t equals 0, start evolving this thing with periodic boundaries, and see how it evolves. Now, the nice thing about the diffusion equation, you actually know what's going to happen to this thing. Diffusion, basically, the energy in the system is being lost. This is what so diffusion often models some kind of dissipation term, some loss, okay, but it's a little bit fancier loss than just simply putting, gamma u here, okay, instead of exponential loss. It's a little bit more complicated than that. So this typical diffusion equation models, for instance, like heat transfer phenomena, where you actually have the dissipation of heat in the system. So that's, for instance, where you can derive this fairly easily. So how would you go about solving this? Well, the idea we've talked about so far is to say, well, suppose this is my solution at time 0, is you would do some kind of discretization, right? You would chop this up into a number of points. And you would say, okay, what happens to each one of these points in time? Okay? Well, since it's a partial differential equation, space and time are related to this relationship here, and so what you need to find a way is a consistent way to talk about how each one of these points evolves. Okay? So first we're going to change it into an ODE system. And the way we're going to do this is we're going to say, okay, the value of u at negative L, let's call it u1. The value of u of negative L plus delta x is u2. The value of u negative L plus 2 delta x is equal to u3, all the way down until we get to the end of this domain, which is u of L minus delta x, oops, which is u of n, and then u of L, which is u of n plus 1. So what I've done is I've called every point by a certain name. Okay? The point on the left. So if I come back to this picture, this is U1, U2, U3, U4, all the way up to, this is U of n, this is U of n plus 1. Now, it's periodic boundary conditions, so if U of n plus 1 is actually U1. So I don't have to solve for U of n plus 1. If I solve for U1, I have it already. Okay, so all I've got to solve for is this point up to that point there, U of n point. So what I care about is the vector U, which is made up of the point U1, U2, all the way to U of n. This is what I want to solve for. Now, how I go about doing that is by doing a discretization of the problem. You can already see the discretization that's happening here just by defining these points. Now, let's talk about what happens if you discretize in the actual equation. So the equation itself is just this, right? It's U of t is equal to k uxx. And we can discretize the same way we did in homework 1, part B. You say, okay, how do you calculate two derivatives with discretization? Well, we wrote down a formula in one of the tables which said that the second derivative is simply equal to u of x plus delta x minus 2 u of x plus u of x minus delta x all over delta x squared. Okay, you derive that formula from discretization. Another way to think about it, if we think about u of m being u of x of m, okay, so in other words, I'm at some point where, remember this x1, x2, x3, these are all my points that I've got, then what this becomes is u of m of t is equal to k over delta x squared, u of m plus 1 minus 2 u of m plus u of m minus 1. Notice, in this discretization, I've taken a problem which was a partial differential equation which had space and time in it all together wrapped up, and I've turned it into now simply a problem that depends on time. Turned it into a differential equation. And this tells me how each one of these points moves. So if you come back over to here, if I want to know what happens to one of these points here, how is it evolving in time? What does it depend on? What this says under discretization, if I take one of those points, it depends upon itself and what's happening to its neighbors. So every point in this thing here depends upon itself and what's going on with its neighbors. This is why, and so this point depends on its neighbors, this point depends on its neighbors. So they're all chained together in some sense. So every single one of these points relies on what's happening to its nearest neighbors. So you've basically, and this makes sense because look, you have spatial dynamics going around, and when you discretize, what that carries over into is this dependence upon your neighbors. Okay? This is what's giving you the dependence on the neighbors, is the second derivative. Okay? So all the dynamics in this whole thing is coupled together. And now what you have is a bunch of differential equations to solve for. Right there. Okay? Now, the claim is that then you can say this is going to translate then down to something just looks like this. You can basically write this problem then, if I collect all the different components into a big vector, which I've already defined u, which is u1, u2, u3, then I get something like this, where the matrix A is going to take care of doing this for us. U. Okay? So, let's talk about how you would actually implement this in a code. Okay? And by the way, we should talk about what does the matrix A look like real quick. If I have a certain point, it depends on itself. The u of m couples to u of m with a negative 2 in front. And it couples to its neighbors with a 1. So the matrix A here is pretty simple. Negative 2 along the diagonals, 1 on the off diagonals. 0 everywhere else. That make sense? Hopefully it does. So negative 2 is the term. It's itself. 1 and 1 are the two neighboring terms. That's effectively what's going on here. I take this matrix A times U, and what it does is it gives me this relationship here. Now, the only thing we have left to take care of is the boundary conditions. What are they? Periodic. So this works fine, except what happens if I'm at point, the first point? So if you come over here, you say, okay, everybody relies on its two neighbors. This point here relies on two neighbors, this neighbor, and there's no neighbor over here. But it's periodic, right? So this point is the same as this point. What's its neighbor then? Here. So U1 depends upon U2 and U of n. Okay, fine. So let's come over here then. If I go to the first point, it depends, the first point, U of 1, which is basically in this first row, U of 1 depends upon itself, U of 2, and U of n. Well, U of n is all the way over there. What about the other boundary condition? If I get all the way to the right here, U of n here depends upon U of n minus 1, U of n, and U of n plus 1. But what is U of n plus 1? U of n plus 1 is U1. Okay, so when you come down to the bottom, U of n depends upon U of n minus 1 and U of 1. That's your matrix. Negative 2, 1, 1, and on the far edges are these 1s. This takes care of your boundary condition. Okay? The proper construction of this matrix, typically the middle of the matrix is easy. Then you have to also put in the boundary conditions in the first and last row typically. And that's the thing you have to make sure to do every time. Okay? So now we need to solve this. This is essentially saying this problem is somehow equivalent to our original problem, which is this here. So let's talk about building this up from a coding perspective. So let's implement this. We want to solve this problem here. And what we're saying is that it's basically boils down to this system here. So how do we solve it? PDE down to a big system of differential equations. First thing you need if you're going to solve this is the matrix A. Okay, so we're going to get a little more practice on using SP diags here. How would you build that matrix A? Okay, so first thing we're going to do, build A. Well, first thing you do with this thing here is you're going to have a bunch of 1s on the off diagonals. So let's make a vector of 1s. Vector of 1s, which is that. This makes a vector. The 1s command makes a vector of 1s of size 1 column, n rows. So this is a big tall matrix or vector. Okay, just with 1s in it. Now, the matrix A, what is it? Well, except for these edges, these two edge points, there are only 3 diagonals that matter. So when I go to write this thing, there's a bunch of zeros everywhere. Only 3 diagonals really matter. So use this spdiags command, which is, again, a sparse matrix, because this is a sparse matrix. There's only 3 diagonals. Everything else is 0. Use the spdiags command to write in 1s over here, 1s here, negative 2. So how do we do that? Well, use the spdiags. This is going to start building the sparse matrix. And all you've got to tell it is where things go. So, first you tell it what are on the diagonals. Well, and remember, you kind of start this way and you go that way. Okay, you start on what are the diagonals down here going through the middle to the other side. We have 1, -2, and 1. Those are what the diagonals have on them. Okay, so I have 1s on the leftmost diagonal, -2, and 1. Those are my 3 diagonals, the values on the diagonals. Okay? Where are these diagonals located? So I'm just going to continue this down here because I'm running out of room over there. Remember, with the spdiex command, the main diagonal down this thing is 0. That's the location. Negative values here, positive values there. So this is on the -1. It's -1 away from the 0 diagonal. This is +1 away from the 0 diagonal. So to place these 3 vectors, you put 1 at -1, 1 at 0, 1 at 1. And this thing is an n by n matrix. Okay? This is a basic implementation of the spdiex. A little bit easier than when we built in class last time. Okay? So what I have is 1, -2, 1 on the -1, 0, 1 diagonals, which is exactly what we have there. Now, what about the boundary conditions? We still have to put these in. 2 ways to do it. One way to say, well, this is the nth diagonal over here, and this is the -nth diagonal. So I could change this around and put them over here. But I'm just adding one number in on these 2 edges. All you have to do is say, well, how about a1n is equal to 1, and an1 is equal to 1. That works fine as well. Okay? Again, the nice thing about the spdiex command, it only keeps these diagonals as information. So if I make n really large, it doesn't store all the values. It just stores the ones I need. Okay? Everybody good with that? That's probably the simplest use of spdiex you can come up with. Okay? And once you have this matrix, if you multiply this, any vector by this, it takes 2 derivatives of it with periodic boundaries. So it's kind of nice. So you kind of, the nice thing about a lot of these matrices that we're building, they're recyclable. It's not specific to a problem. I want to take 2 derivatives in x. Well, here's my matrix that does that. Right? And you can reuse this in other codes, because you always have to take derivatives all the time, in x or y, whatever. So this is a really nice, once you start building these things, it's great. Like the matrix A that we built for the homework 2, that takes 2 derivatives in x, 2 derivatives in y. You have it built once, you can use it all the time. Okay? All right. Once you build this matrix A, you want to go solve this, you say, well, I need to give some initial condition to this. At time 0, what does it look like spatially? Okay? So, that's step 2, initial conditions. So, I don't know, what do you want them to be? How about U0 is equal to, you could make something like a Gaussian initial condition. For instance. So now you have initial conditions. Notice what this does is it says, okay, my initial condition over this domain from -L to L looks something like this. So it's defining every single one of these points according to what the value is here. With those 2 in hand, you now basically are ready to start solving that problem. Essentially what the initial condition does, right? What it does, it tells you, I know the initial value of U1, U2, U3, all the way to U of n. It initializes every single one of these points. When you solve differential equations, you always have to have a starting initial value, and then you let it run. You've just done that. Okay? All right. Without specifying initial conditions, what we do know about differential equations is that I have these arbitrary constants in there. So in effect, I have an infinite number of solutions. Well, you know, the computer doesn't handle that very well. You need to specify for the computer exactly what you want it to do. Okay? All right. Now, let's solve. So if you're going to solve this thing, all you have to do is call some kind of ODE solver. So you've already done this for part, you know, the first homework, but now you're solving a PDE with it, and here's what you would do. Standard command works like this. ty is equal to ODE 45. You call some right-hand side. You throw in your time span. And like, for instance, time span might be, I want to solve this thing. I want to solve it from 0. There's a couple ways to define t-span. You can just give it 2 points. I want to solve it from 0 to time 10. So you could put something like this. 0, 10. It'll solve it for you from time 0 all the way to time 10 and give you all the steps in between. You could also do something like this. How about we'll do t-span is 0.5, 10. I want you to solve from 0 to 10, but give me the time steps every half unit of time. So what this does is it says, okay, I solve it, I'll give you data, but I'm only going to give you 20 pieces of data. 21, excuse me, right? I'm going to give you the value at 0, at 0.5, at 1, 1.5, 2, 2.5, so forth. Sometimes this is really handy. When you run things, in fact, for the code you're running for homework 2, you don't want it to spit out everything it calculates. It's way too much data. Okay? Because if you tell it to run from time 0 to 40, if it takes time steps of like 10 to -3, how much data are you going to get if you solve it from 0 to 10, for instance? If it's taking DT to 10 to -3, it's going to give you 1,000 two-dimensional plots per unit of time, and you're going you're going to get 10,000 slices of data. Your computer will not like this. Okay? Especially when you try to plot this, there's way too much data that you have. It'll really bog down the computer. The last thing you want to have happen is you get yourself in a situation where your chip that you're running your code on is running out of memory, so it's having to access the hard drive to write stuff to. Now, when you're in that, your code is just going to tank in terms of speed. Okay? You want the full computation to be done on the chip, never leave the chip. As soon as it does, I mean, it slows down by a factor of 1,000, or I mean, it's some huge amount. Okay? So this ensures you how much data you want to keep, and so make sure that you also don't, basically fill up the thing with too much data. So anyway, different options for t-span. Now, the next piece in this, usually you specify, so you give the initial condition, and the next piece you specify the tolerance. This is something you played around with in 1D of the homework. But if you don't want to do anything with the tolerance, square brackets. Okay? So I'm calling this thing, I'm sending in my time I want to solve it for, my initial conditions. I'm not going to mess with the tolerance. And in the right-hand side, what do I need? Well, here's my right-hand side. I've sent in some initial conditions, but I still need k, delta x squared, and a all in there. Now, the traditional thinking is that somehow I've defined all these things outside of this ODE loop, but they need to be in this ODE loop in order for you to calculate it accurately. So what you can do is just pass them in. So comma, and then pass in k, a, and call it dx. So that's what you would do. So after you've the tolerance slot, you can pass in as many variables as you want to the code. Okay? Now what this is going to do is going to call this function right here, and then it's going to start using one of the your fourth order Runge-Kutta, for instance, to start solving for this thing. So what does this right-hand side function have to look like? Well, first of all, if I call it RHS, what the computer does is it looks for a file called rhs.m somewhere in the same directory. Okay? So what should rhs.m look like? Function RHS is equal to RHS, and what's coming in here is your t-span, your u, your dummy, your k, a, dx. By the way, you don't have to call them the same names. I did, but the order is very important. If you have k, a, dx, it's going to read as k, a, dx here, regardless of what I call them here. So don't change the orders here and here. That'll be bad for you. Okay? And then for the right-hand side, for this problem, it's as easy as just saying, well, my right-hand side is simply k over dx squared times a times u. That's it. Algorithmically. So really, this is very little difference between this and what we did in homework 1. What you've done here, this gives you the way to update all of these n first-order differential equations that are all coupled together. And how do they couple together? Well, the matrix A takes care of coupling them together to the nearest neighbors. Okay? And this will just run through. Calculate, calculate, calculate. We'll spit out the values. And remember, the t-span is the current time in the right-hand side. T-span on the outside is some specified vector. But in here, t-span is currently where are you in time. Okay. Any questions on that? Y'all good? All right. Everybody awake? That's the only problem with 8:30 classes. It's actually worse in the afternoon because everybody needs to take a nap. But I think probably 10:30 is like the ultimate best time to take a class. Or to teach a class, really. It doesn't matter when you take a class, right? But when you teach a class, it matters, because then you get more people awake. So, all right. So that is the standard algorithm. What it spits out, by the way, let's talk about that. T and Y. T is the time. When you solve this thing, if you put in t-span with 0 to 10, it gives you all the times it actually has solutions for. If it took steps of 0.01 in size, this will spit out 0, 0.01, 0.02, 0.03, 0.04, all the way down. So it gives you the actual times it took, all the way up to time 10. If you use this command here, t-span was 0, and steps of 1/2 to 10, what t is t is 0, 1/2, 1, 1.5, 2, 2.5, 3, okay, ordered. Corresponding to this vector is y. Y is now really huge. The rows of y are your solutions at the corresponding times. So this thing is a big column vector with increasing time. And this y, as you increase in time, this is what the rows do. And across here are your n values. So this is x, u1, u2, u3, u4, u5, u6, all the way to u of n at time 0. The next row is u1, u2, 3, all the way at time delta t in the future. Okay? All the way down to the very last thing, which is your solution, u1, u2, u3, all the way to u of n at the final time, let's say 10. Okay? So now when you start thinking about grabbing data out of here, remember in homework 1, you were actually grabbing y1 and y2. You were grabbing the two components. What you really want to do is, this actually is your whole solution. You can take that and plot it, because that's u1 through u of n at time 10. So you just take that whole row, plot it. Okay? So you grab it, use the end command. So you say, okay, I want this whole row. All right, so go to the last row. Grab the whole thing. Grab every column. That's going to be your, call it UF, your final solution. Okay? And manipulate it accordingly. All right. All right, so now let's talk about making a little bit harder problem. Everybody okay with that so far? Excellent. For those of you at home, the enthusiasm in this room is sky high. It's like a party in here, right? We're going to get on TV to say that. Now, don't pan out. All right. Now we're going to do a little bit harder problem. 2D problem. So let's start over. Let's do the same problem, but 2D. And in fact, for 2D, it's very much the same architecture in your code. Okay? So we want to do the same architecture, but there are some significant differences. And this is going to be important. First of all, it's two-dimensional, so we're going to compute on some kind of grid now. And we've already talked about this. So now instead of every point on a line, we have to talk about every single little point on this grid. And we have to update its value. Okay? Fine. That's not that big a deal. However, when you start defining vectors like what's my x and my y, on some level, your computer has no idea you're solving a two-dimensional problem. Right? You mean x to go this way and y to go this way. Does your computer know that? No. So you have to teach it. So we'll show you how to, we'll talk about how to do that. It's going to be very important for what we do. Okay? Not only that, but it's a vector. And I mean a matrix. And when you actually solve this thing, right, in the computer, you've got to turn that into a vector. So what you do is you stack them. This is what we talked about in class, which is, you know, you keep track of all these values, and now you take that piece, you stack it there, take this piece, you stack it there, take the third, stack it, and you keep moving across and you keep stacking it. So this, which was n by n, so it's n by n matrix, now becomes an n squared by 1 vector of your data. In particular, when you discretize this thing is going to turn into ut is equal to where u is u11, u12, all the way to u1n, and then u21, u22, all the way to un, and so forth. So this is the stacking. So this is row column. So first row, or sorry, so it's 1, 1. So it's like x and y coordinate. 1, 1, 1, 2, 1, 3, 1, 4, all the way to u1n. And then you go to u21, u22, all the way up like this. So you just stack everything. And I'll show you how to do that right now. And this is what you're solving now when you discretize. Now, here's a matrix A. We've already built this. This is what, last two lectures ago? This matrix A, we have to take 2 derivatives in x, 2 derivatives in y, and we're assuming periodic boundary conditions here. And if you take something that's 2 derivatives in x, 2 derivatives in y with periodic boundary conditions, that is the matrix A that we built already in class. Okay, so that's in the notes. I have that. Okay, but let's talk about some general other things here. So first of all, build A. We did that. That's equation 2.113, and then we built it in class, I think, during that lecture. Okay? Second, generate initial conditions. So you see, we're doing the same pattern as before. But now, your initial conditions, right? Might be something like this, some two-dimensional structure. What do you do to how do you define a two-dimensional structure? Okay? So for instance, that might be a Gaussian lump in 2 dimensions. Can everybody visualize that okay? Okay. So first of all, you define your x and y variables, and this is where we're going to start talking about reshaping and stuff. So let's call it my L in the x direction, let's say it's 20. My L in the y direction, let's say it's 20. So as I've said, this is 20, this is 20 here. Okay? And let's chop up x into 100 points. Let's chop up y into 100 points. For a lot of what we want to do, chopping it equally in x and y is a good idea. Okay? Now, remember, if I have n points this way, n points this way, how big is the vector I'm going to create out of this thing? N squared by 1, or the reshaped vector is going to be this size, right? So if I take this thing, has a certain number of points, n of x this way, n of y this way, when I reshape it, it's going to have nx times ny points. If nx and ny are the same, it's just n squared. Okay? Now, what are my x coordinates then? It's periodic, so I define a vector x2, which is a linear space that goes from negative lx over 2 to lx over 2 in n of x plus 1 points. So when I say I want 100 points here, what I mean is I'm going to solve for 100 points. The last point is the same as the first. So really there's 101 points. Okay? But the last point is the same as the first. So, but from this point of view, what this does creates a linear space which goes from negative lx over 2 to lx over 2 in 101 points. The last point is the same as the first. And all I care about is the first 100 of those points. So you say, what I really want is x is equal to just the first 1 through 100 points. Okay? Now you do the same thing for y. Oops. And then you get ny. And y is equal to y2, 1, 2, and y. Okay? So we just defined our x and y vectors. This defines this grid we are working on over here. Right? This grid, we chop things up in x, we chop them up in y. Now what we've got is basically we've defined where all these points we have to solve for are. Okay? The finer you chop it, the more resolved of a problem you have. But the finer you chop it, the bigger this matrix you're working with, or the bigger these vectors and matrices you're working with. Okay? That's where the slowdown can happen. All right? All right. So, how would you define some initial data? Because this is part of what we're trying to talk about here. What is my initial condition? Suppose I wanted to do a Gaussian in x and y. So you could say, well, how about something like this? That kind of looks like it would make sense, right? X and y, x is chopped up, y is chopped up. But the computer at this point, when you do something like this, has absolutely no idea that you have in mind that x goes this way and y goes this way. You have it in your mind. Obviously, x and y do this. Okay? Teach the computer. Help me help you. That's what you say, the computer, right? All right. That was the only good movie Cuba Gooding Jr. did, I think. At least that's the only one he was good at. It was Jerry Maguire. Help me help you. Okay, so we are going to help ourselves help us ourselves, okay? Here it is. Use what's called the mesh grid command. Let's define a new variables x, big Y. And when you say mesh grid, x, y, what mesh grid says, oh, you mean x and y. You mean that x and that y. It now knows what you're talking about. X now is a matrix, and y is a matrix. X is a matrix that along all these values, it goes from negative L over 2 to L over 2. Right? So the value here is negative L over 2, goes down to 0, goes up to L over 2. But for each one of these slices. Okay? So if you were to go along a slice there, the value of this thing is minus L over 2 over here, L over 2 over there, so it does something like this along each one of these slices. And big Y now is, well, that goes from negative L over 2 to L over 2 for each one of these. You can just plot them, take a look what they are. But now this is what you want to work with, big X and big Y, because now they have direction. They know that they are supposed to be related to what you have in mind as X and Y. And by the way, if you want to mesh grid 3 dimensions, say X, Y, Z, X, Y, Z. Okay? It will keep these directions for you. So once you do that, now you can say, okay, now define some initial condition. You could say my initial data is equal to capital X squared minus capital Y squared. And what this now does is it creates a initial condition that looks like a Gaussian sitting in there. Okay? Now, there's one last thing that needs to happen, which is this initial condition is a matrix. What do we need to throw in to OD45? A vector. So you've got to say, well, I've got this. This is a matrix of initial data. I need to send in a vector of initial data. The last thing you need to do then is to use what's called the reshape command. So let's call this capital U naught. Is this thing here. And then little u naught is going to be the reshape of this. And there's a nice thing about this. There's a reshape command in MATLAB. The reshape says, when you come into this thing, or when you have this initial data, take this thing and then write it out as a big old matrix. Stack it up like you have to. So the reshape, you say, what do I want to reshape? Capital U naught. And how do I want to reshape it? Right now, it's n of x by n of y, and I want to reshape it into a one column with n components, where n is n of x times ny. That just stacked it all for you. Okay? Now, the right-hand side function now, step 3, solve, same format as you did before. Absolutely the same as we did for the one-dimensional case. But the matrix A now is different, and so is the initial conditions to this reshaped version. Okay, but you call it. And now here's interesting. What comes out? Y is this huge matrix. Y has not just U1, U2 all the way to U of n. It has U11, U12, U13, U21 all the way up. So this thing here has n squared. It has n components across it, which is your n squared, essentially. So if you cut up 100 points this way, 100 points that way, this has 1,000 points. It contains your data as a vector. What you're interested in maybe is the last row of this thing. And you get this thing out and you go, oh, okay, well, I've solved this thing, but it's a big vector. I want to plot it in 2 dimensions because it's a 2-dimensional problem. But I have everything now in this big vector. Well, how do you get this thing and then get something meaningful out? Here's what you do. You grab this last row. You say, my solution, let's call it little u of f, which is the final solution. Can you guys see that, actually? Okay. All right, you can see it up there. Great. So if you do that, let's grab the last row of this thing. That's all we did here. UF is the final solution. Grab the last row. What we want to do is say, okay, now that I have that, I'm going to define U, capital U of f, which is going to be my actual solution, as do reshape again. What am I trying to reshape? U of f. And what do I try to reshape it into now? It's this big old vector. So now I want to reshape it back to a matrix with n of x rows, n of y columns. So now this says, take this thing which is a big, take this thing which is a big vector, reshape it back into what it was originally. Then you can plot it. Okay? So you have to reshape before coming in, reshape when you come out to actually visualize the data. Okay? All right. So those are important commands because with 2- or 3-dimensional problems, this constant going back and forth between this stuff and this stuff is happening all the time in your code. The reshape command takes care of it for you. So that's nice. So you don't have to work that hard to do it, but you'll have to do it pretty often. Okay. Why is this called the method of lines, by the way? In everything we've done so far here, when we've done these kind of structures, essentially what we're doing, think about the one-dimensional problem. If time's running this way, you're specifying some initial condition at time 0. You're taking this thing and you're breaking it up into some negative L over 2 by discretizing a bunch of points. And what you're essentially doing, you're saying, I start off with an initial condition, and by using this OD45, what I can do is I can step forward delta t into the future with a simple little algorithm, which is to say, my point in the future depends upon these 3 points. That's what the matrix A does, right? The matrix A, which takes the derivative, says, I need 1 of this, 1 of that, minus 2 of my current point. So what it allows you to do is these 3 points are responsible for generating the future point there. And so any one of these points, you can update the whole solution at delta t in the future by basically using the values at delta t right now. So method of lines refers to, I have a line of solutions. Using that line, I can generate a new line of solutions in the future. And with that line, I could generate another line of solutions, and another line, and so forth. That's in the one-dimensional case. In 2 dimensions, same idea. But now, in 2 dimensions, what you're saying is, now I have 2-dimensional solutions, right? So you chop this up in x and y. So this is times 0. That's delta t into the future. What you do if you want to get the point in the future, you rely on the neighbors. So you go back down, you project this point to where it was down here. You need that point and its neighbor. So using these 5 points to update that 1 point in the future. So you can take this whole plane or line and update this plane. Take that whole plane, update the next plane. Okay? What I need is one of those illustrative little chess sets, you know, the ones with 3 levels. You could just, that'd be cool. Okay. Anyway, that's it. These simple examples, we'll build on that quite a bit in class. I think the important thing that we're starting to illustrate, especially since the homework's going to be due on Friday, is that when you start doing this, you start with homework 2. You're going to have to start thinking about it's a 2-dimensional problem. When I come in and out of the ODE solve, I always have to have this 2-dimensional data as a vector. And so you have to constantly be reshaping. The actual algorithm is actually not that hard, but you know, you have to take care of these issues.